Hello students. Yesterday we have seen about dual nature of particles and radiations. Today we will talk about atomic spectra of particles. You know that matter contains atoms in which at the center there are protons and neutrons called the nucleus surrounded by electrons moving around the nucleus. When an energy is given to this electron, it jumps from a lower energy state to a higher energy state, and it cannot remain there as it is an excited and unstable state. The electron jumps from the higher energy level to the lower energy level, thereby emitting radiation. Such type of things happen in the discharge tube, as you have already read. Vacuum tubes, of course, electrons are emitted from the cathode. In the discharge tube, the whole amount of gas is evacuated and a little amount of gas remaining at very low pressure. There is a cathode and anode. A high potential difference applied between these two electrodes. When the current passes through the gas, the gaseous system emits radiation in the form of some color of light, which contains many wavelengths. These, when passed through the slit and focused on a prism, here we have seen in this is the discharge tube, at which inside which there is a gaseous substance at very low pressure. It emits radiation passing through the slit and focused, and then it is passed through the prism, which will separate the wavelengths. Prism is an instrument in which when the wavelengths pass, they will be dispersed, separated, because the bending angle is different for different colors, so they will get separated. When they fall on the screen, they will form an image of the slit. So that is what about the discharge tube. When they form this image, with the study of this image, which is unique for a given gas, under a given circumstance, it is unique. So we can also identify the composition of many compounds, many gaseous elements like that. The spectrum so obtained consists of a bright background. Here there is a bright background with dark lines, and here there is a dark background with white lines. When dark background with white lines, it is called emission spectrum, and bright background with dark lines, it is called absorption spectrum. When white light falls on a gas and absorbed, then the spectrum has bright background and dark lines. Then it is called emission spectrum. So both these types of spectra are utilized for studying the gaseous substance inside the discharge tube. Now regarding hydrogen, hydrogen has a single proton and a single electron revolving around it. The hydrogen atom, when subjected to external energy, the single electron jumps to higher energy levels. While jumping back to the ground state, it emits radiation in the form of dark lines. That is absorption spectrum. Now, whether it is an absorption spectrum or an emission spectrum, the position of the lines, that means the wavelengths emitted, is the same. Now each line corresponds to one wavelength, that we must understand. Bohr's atomic model gives us this formula: 1 by lambda is equal to R, that is Rydberg's constant, into 1 by n1 square minus 1 by n2 square. N1 is the ground state and N2 is the excited state. Here lambda is the wavelength of light emitted, forming the line in the spectrum. N1 is the energy level of the ground state, N2 is the energy level of the excited state. The whole lines we receive when an electron jumps from second energy level to first energy level is named as Lyman series. The next series is obtained when the electron jumps to N2 level from upper levels, that is N3, N4, N5, like that. This is called Balmer series. The next level is obtained when these electrons jump to N3 state from higher energy states. This is the Bastian series, and to N4 state from higher energy levels, bracket series, and to N5 level from higher energy levels is called Fund series. Each spectral line has got a particular wavelength lambda pertaining to that spectral line, and it follows this equation. N2 is the excited state and N1 is the ground state. Now for the Lyman series, if we write this equation, N1 is equal to 1 we put, then it will be 1 square, and N2 we can be 2, 3, 4, 5, like that. For the Balmer series, we will put N1 is equal to 2. Similarly, for the Bastian series, we will put N is equal to 3. For the bracket series, N1 is equal to 4, and for the Fund series, N1 is equal to 5. These formulae are used in getting the wavelength of the emitted radiation. Thereby, we can find out which gas is incorporated in the discharge tube. A particular gas has a particular spectrum of lines. It cannot vary from that. So, from the spectrum, we will infer which gas is inside. Now we have another formula, Rydberg combination principle, after the scientist named Ritz and Rydberg. This relation is a relation between spectral lines of all atoms. The frequency of unknown spectral lines of an element can be obtained by addition or subtraction of frequencies of known spectral lines. Like for example in this figure, an electron jumping from EI state to En state, and another electron jumping from Em state to En state, another electron jumping from EI state to Em state. So we see this total energy should be equal to this energy plus this energy. Now H nu is the energy formula, energy of radiation emitted. H nu In is the energy of radiation emitted when the electron jumps from ith state to nth state. Likewise, H nu Im is the energy emitted when the electron jumps from I state to M state, and from M to N it is H nu Mn. Now as you see in the figure, H nu In equal to H nu Im plus H nu Mn. Here we have written the same thing. So H nu Im will be equal to Ei minus Em, H nu Mn equal to Em minus En, and if you want to find H nu In, you just have to add these two, Ei minus Em, Em minus En, you have to add. In that Em will go and Ei minus En will remain. So H nu In is equal to 1 by H. Nu In will be equal to 1 by H into Ei minus En. So if you know the values of H nu Im and H nu Mn, you can find out nu In. So nu IN is the frequency of the radiation emitted when the electron jumps from ith state to mth state. Again I repeat, it is Rydberg combination principle which allows us to find out the frequencies of unknown spectral lines from known spectral lines. Today we finish here. Tomorrow we will be with you again for Rutherford scattering experiment. Thank you.